It started recording, and move this window out to the side. All right, and start my stopwatch before I go on forever. Okay, and yeah, so what's interesting is that for most lasers, steady state. Uh, okay, so let me just ask this question quickly. How long do you think it takes for most lasers that you think of or you've seen? How long do you think it takes them to establish steady state?
Probably less than a second.
You're absolutely right. I mean, like, in fact, not even a millisecond for most. A microsecond is all it takes. And you know why? Because if you recall, in your one of your quizzes, you just worked out that the excited state lifetimes were in the nanoseconds. Remember, 16 nanoseconds, 27 nanoseconds. So steady state, all it takes is a few bouts of stimulated and spontaneous emission. So maybe 10 cycles, maybe 100 of 227 nanoseconds, let's say, for rubidium, if rubidium is involved in your laser. So 16 nanoseconds, 27 or whatever, 100 times, and steady state is established. Like, you got some absorptions, emissions going, and everything's established. So a millisecond at most for many some solid state lasers, but very, very quickly. So this is a very non-restrictive condition here. What's happening in steady state? And so in steady state, all you do is you say, you look at the equations and you say steady state always. I mean, what I like about this cartoon model is it also tells you about other things, that always, whenever you're interested in steady state, you just take the time changing term and set it equal to 0. Okay, so this is 0, and so is the rate of change of the excited state atoms. And so now, let's look at the Q equation. So now that means that in steady state, the gain coefficient times the number of this term here, A and Q, gain coefficient times the number of atoms in the excited state times the intracavity photon number is equal, to the loss rate there. And so right away, you can from this write down that the number of excited state atoms in the steady state, is equal to B over A. Okay, so that's an interesting thing to keep track of. That's a condition. Okay, in the steady state, you need this, and also you realize that you just set in steady state, you set this equal to 0, which means your number of intracavity photons are no longer increasing. They're not changing anymore. So this is in the steady state. The gain term, the gain equals the loss. So this is not only a steady state, but also a threshold requirement. So I'm actually going to do this also. Okay. So this is implying it's a threshold, meaning that you need to have your gain equal loss at least, right? And then at that point, yeah, number of intracavity photons are not increasing anymore, but you've achieved lasing, and so it's a threshold value, and so this yields a threshold requirement. And so everything I just said, I'm just writing it down, yields a threshold requirement because you notice, threshold requirement for the laser. And this is such a simple consideration that we just did for the laser, because, and that's what I was just saying, that because if your number of excited state atoms drops below this value, okay, then what happens then? Then if that happens, then your, this is the value at which the rate of change of intracavity photons is 0. Well, if this drops below that value, then the rate of change of intracavity photons will actually drop below zero. And of course, if this happens, that means the rate of change is below. So now you're losing intracavity photons, and of course this will kill, which will kill laser action. Okay, so this is a threshold requirement as in the steady state. Okay, so we know that, and now what I'm going to do is take this value, and so now what I'm going to do is take n steady state threshold and plonk it into the dn over dt equation. Why? And why? Because I'm going to, so it's going to show up here and here, right? And by doing this, I will obtain a threshold value for the pump, meaning to obtain a pump threshold requirement. Okay, so let's just do that. Everyone can still see this. So now dn over dt is 0. So the pump, therefore, must equal spontaneous emission rate times n, which we just solved that, and plus, so pump in the steady state is this, plus the other term, which is A and Q, right? And that's steady state. So, okay, so let's just put in that value, right? So it's F B over A plus A, and N is B over A Q, right? And so you see something cancels out. And so what you find is that Q, so if I solve for Q, okay, and the reason I want to solve for Q is that it will become clear in just a moment. So just stick with me for a second. So I'm solving for Q. So this is equal to P. So Q is therefore Q is therefore P over B minus F over A. Okay, and the reason I solved for Q is that it's the intracavity photon number, and this cannot be negative. So that implies that P over B must be greater than F over A, okay? And so this tells me that there is a steady state, this gives me a requirement now, okay? So this is a threshold requirement that, that's the threshold requirement for the pump, okay? And of course, it has to be greater than that. And so the equality, the threshold condition, I suppose, so threshold condition is where the P, the pump rate, and this was all steady state, right? This is all steady state. But steady state threshold, that happens when it's equal, right? So it's B over AF. And you recall that B over A was, of course, just n steady state threshold, right? So this is saying that this is n steady state threshold times the spontaneous emission loss. Okay, so this is another condition. And so basically what this is saying, it's not something, that is sort of, this is in a way what you would expect. What it's saying is that if I write this out in English, it says the threshold pump rate, okay? Because to make a laser, you always need to know what the condition is for, like, do I have another laser to pump it? Like, I mean, if I'm making a dye laser, for example, well, then do I have a laser that's capable of pumping it? You know, and it turns out that for dye, the argon ion is a great choice as a pump laser. On the other hand, if you say, I want to make a laser from beer, okay, well, yeah, you can, but what's the ideal laser that will pump beer well? And, so it would have to satisfy this sort of condition. And I think people have made beer lasers. I think they used some kind of infrared laser. I will have to look that up to know exactly what they did. But anyway, so the threshold pump rate, so that's your left-hand term, and it is simply the F. So this is the spontaneous emission loss rate, per atom. That's the F. And then the N sub SS is just the number of excited state atoms at threshold. So it makes sense, right? It's the spontaneous emission loss rate per atom, meaning per excited atom. Obviously, only an excited atom can spontaneously emit. So, I mean, this makes sense, this equation, that you need to exceed your pump rate. You must replenish, you must replenish faster than your losses due to spontaneous emission. Okay, so the losses due to spontaneous emission are the spontaneous emission loss rate multiplied by the number of excited state atoms that are present at threshold. Okay, and so that's your threshold pump rate. Now, so we obtained very simple, equations here. I guess this is the one that summarizes what we just discussed. In this, I've spent 15 minutes talking, 12 minutes actually. But this is the important condition that we just derived, that yes, there is a threshold pump rate, okay? And so from here on, now, what I would do is use these ideas to, write out an equation for a 3-level atom model. First of all, I need to show you why a 2-level atom does not work. So we need to write out equations for a real, for a real atom, I guess. Take these ideas forward. It turns out that there are 2 terms that I still need to define. And let's see, do I have them written out here? There are 2 terms that I need to define. And one is, one of them I've introduced already, but we will now look at it in more depth, because after all, that's what it's all about. It's the gain coefficient. Okay, this gain coefficient, we'll talk about this more. And other than that, there is the concept of photon flux, which is important. Photon flux is important because, the Q and the stimulated emission is all wrapped up in that photon flux term. So I'm going to stop here, and once again allow, well, actually we're going to stop here and allow everyone a 2-day break. And Thursday we're going to come back to these things. So actually at this point, let me just say I'm ending the class, and any questions at all, I'm here. So I can't like when we're sitting in class, I can't point at someone and say, hey, how are you doing? In this case, I have to just sit with my wares for display and my shop open and look around expectantly, waiting for any questions that anyone may have.
Professor?
Yeah.
So, what is the like the NSS T, like what's the T after NS? Like,
Oh, this one here?
yeah, I understand N means the number of atoms in excited state, but and the SS represents the steady state,
Right.
right? So what's T mean?
T is the threshold, meaning that not only is this the steady state value, but it also needs to be, this is the minimum value that it should have in order to
Um,
yield lasing. Because if this value drops below B over A, then that would
uh,
mean that this rate of change would actually become less than zero.
so the addition T means the laser is also in uh, uh,
Yeah, I mean, so, okay, you are right that this cartoon model only tells me about the laser operation at threshold. That's what it turns out. Like, this cartoon model is too simple to tell me about how a laser would work above threshold. The lasers that you use in the lab are above threshold, meaning uh,
okay.
you saw in the video that Kifang made how you keep turning up the current, and up till about 45 milliamps, it was just like a lamp, and there was a sort of a bit of a glow, but at 45 milliamps, suddenly the current jump was, it exceeded a certain threshold, and then the laser just started lasing, and the light became suddenly bright.
Okay, so T means the laser is just right at the threshold.
Yes, and this
Correct.
simple cartoon model only tells me what happens at threshold. So steady state laser operation at threshold. That's an important
Okay,
point.
okay,
It
okay.
doesn't
Yeah, I
really
see.
tell me what it means to be above threshold.
Okay.
And in the lab, when you turn the current up above 45 milliamps, I think the maximum current was allowed before you burn the diode out was like 140 milliamps. And a preferred operation current is also specified by the manufacturer, and in the lab laser it's something like 80 or 75 milliamps. And so then it's above threshold. There's nothing about the lamp left anymore. The stimulated emission has completely overtaken everything else, and it's a it's a it's a pure laser at that point.
Okay.
Yeah, it's a good question. Thanks for bringing that up, because that limitation of this cartoon model is an important one. Other questions? Did Andy get his mic figured out? Maybe I should type him. Maybe I should type to him. I have his text actually. I could text him. Uh, Let me stop the video, because otherwise, I mean, I wonder, like, how, I mean, by the way,